Good morning and welcome to the lightning session. So I'd like to talk about a topic which is a little bit different from most of the topics that we've been hearing about up till this point at the Ray Summit. And that is regarding accelerating campus computational science by using Ray. So it's a use case example. I'll talk about a couple of specific use cases of interest. And first of all, I'd like to introduce myself. I'm Jack Brassil. I'm at Princeton University, where I have two roles. I'm the Associate Dean for Research, so I'm concerned about the research that's going on campus-wide. And in addition to that, I am a Senior Research Scholar in the Department of Computer Science. So let's dive right in. So what is my goal as a Dean for Research at Princeton? Very much interested in supporting a mix of high-performance computing and AI, ML workloads across campus. That mix is changing as we speak. It's very hard to keep up with the balance of the different workloads that are happening from moment to moment. But to step back and look at it, what's happening is that we have a diverse population of computational scientists, all who need Python, both horizontal and vertical scaling, to make their science advance. The AI ML researchers on campus need both tools and training, particularly in disciplines that have not historically been places where much of the AI and ML workload has been coming from, such as the humanities and social sciences. There is an interesting other phenomena going on with infrastructure, as we're all competing for infrastructure. And of course, as you know, on college campuses, infrastructure is perhaps more limited than what you might be used to with the different institutions that you work for. So hardware and getting access to hardware is tricky. So what we see is that there's some degree of divergence of the clusters that are being spun up on campus, where we have historic high-performance computing clusters, but increasingly we're seeing groups of researchers who need, essentially fresh new hardware for their ML workloads, spinning up dedicated systems just for special topics like running their LLMs. So a possible solution to this, and what I'm investigating, is can Ray help here with this challenge of mixed workloads that are both high-performance computing, modeling sort of conventional workloads being increasingly taken over by ML workloads, but in fact, the conventional workloads are not really going away. So this work is being funded by the National Science Foundation. It's actually a project that starts, interestingly, today. I'm the PI. And the particular project program area it comes from is what they call campus cyber infrastructure. So it's about helping campuses really come to grips with their cyber infrastructure challenges. Okay, so when I talk about researchers on campus, they execute on campus clusters, but they also execute on systems that go far beyond what we think of as traditional campus infrastructure. So it starts with public compute clouds, where some operate Department of Energy leadership class systems. In some cases, NSF shared supercomputer centers, such as those at TAC and NCSA. Specialty NSF-supported test beds and experimental infrastructures, and I'll talk about one today called Fabric. The state of New Jersey, where Princeton is, they, like many other states, are spinning up a statewide and sort of regional AI hub. So it's another platform for researchers on campus to use. Of course, there's conventional high-performance computing clusters, as have always existed on sort of research-intensive campuses. And as I mentioned, dedicated AI GPU clusters being spun up increasingly as sort of independent entities from the high-performance computing clusters. And of course, a lot of development will continue to take place on desktops and even small kind of departmental clusters that are not really open to all the researchers on campus. And finally, of course, we have researchers who are interested in applications that are much more sort of IoT-centric, and they're interested in building reinforcement learning kinds of applications in those settings. And they think about using, downsizing to platforms such as NVIDIA Jetsons or even potentially Raspberry Pis. So a whole range of different platforms we have to work on. So that's addresses kind of the complexity of the solutions that we need on campus to make it as simple as possible, hopefully seamless, to move from one environment to another environment. Okay, so I'm going to talk about two use cases quickly just to show you how different the applications might be on a campus setting. So one is looking at evolutionary biologists on the Princeton campus. So many of these biologists happen to do some field work at a research station and conservancy that is co-operated by Princeton University in Kenya. And these folks are interested in building reinforcement learning applications to basically build sophisticated kinds of actuated camera trap systems to be deployed in the field in this kind of setting. The good news is that when that data would get captured by these IoT devices and camera traps, that whole back-end ML system to study that data actually already exists. There's a system called Imageomics at Ohio State University. So that is already in the pipeline for workloads coming from places like the Impala Research Center at Kenya, the images that are generated there. So what we're interested in this kind of use case setting on campus is to find some simple software platforms that will help us with the end-to-end research, simplifying it. And lots of the evolutionary biologists don't have that much computer science training. So if we can build, and rely on tools like Ray to help them deploy their systems from simple camera trap RL systems all the way up to backends that are sophisticated like the Imageomics platform, that's a win. So that's use case one. Another interesting platform that might be of more interest to the many computer scientists who are joining this audience today is an NS-supported testbed called the Fabric Research Infrastructure. So Fabric looks like an internet playground for researchers. It operates and interconnects 35 different institutions, primarily in the United States, but also overseas. What it allows the different institutions and universities that are connected to it, what it allows folks there to do is, for example, connect to major instruments, for example, CERN, and pull data from those instruments, and perhaps feed it directly to compute clouds or other university destinations that we have in mind. One of the nice things about Fabric is it allows us to build sort of collaborative teams across campuses safely. So I can connect my infrastructure on Princeton to other infrastructures and other instruments on other campuses. So if you want to learn more about Fabric as a resource, go to whatisfabric.net and you can learn much more about that. But what I've been doing is deploying applications using Ray across this fabric of 35 institutions around the world. So I'll give you an example quickly of how I spin up those applications so you get a sense of just how easy it is. So the first step, of course, is I have to create a topology, a virtual topology over that network. So the code in the panel shows you how simple it is. In this case, I'm connecting only two institutions, Princeton University and the University of California at San Diego. Both are connected to the network and have resources to offer. The second step is just spinning up VMs or attaching to connected computers on campus, the different endpoints that I've selected. So the panel also shows the code how to do that. And in this particular code example, I'm just spinning up 4 different virtual machines, 2 on each campus. And then if I want to, say, run a Fabric application, it's time to push up the executables that I'd be running and the tools that I'd be using to inspect those outcomes. And then finally,
It's runtime. The panel just shows running some Ray benchmarks, but I'm generally running more interesting and comprehensive kind of applications than just that. Let's see if I can show you an example of what I was doing just this morning. You may see something which is familiar here, which in the top terminal box, I'm just running some standard Ray tutorials, but these are actually being run in Amsterdam on some GPU nodes, and the topology is shown below in the figure. It's just very simple. This is actually local just to the Amsterdam site of a couple of nodes that are running this torch training application, which is a standard Ray tutorial. And it could be running anywhere. So now, why is this interesting? Well, we have students, for example, who might need resources, so it's great that they can reach out to other institutions and grab those resources. Or they might be trying to do something as simple as, in this case, discovering some new GPU hardware which they haven't used before and seeing how effectively that hardware works. In this case, this is some NVIDIA A30s that I happen to rely on. So let's go back just to finish up. Back to my slides. I already talked about how to spin up the Ray application in that setting. So now I've talked about two use cases. One is evolutionary biologists studying wildlife, learning about wildlife, and the second is computer scientists, for the most part, studying Ray in the wide area and Ray in different settings that we can attach to. So just to summarize what this whole project is about, because it's far different from lots of the things you'll be hearing in later talks, I'm interested in characterizing Ray performance across multiple diverse academic platforms that are available to university students. I'm also interested in understanding how Ray can streamline teaching distributed computing frameworks to students, including students who are coming from communities that are historically not where we see ML and AI applications coming from. And finally, I'm here today to reach out to you to seek to build and strengthen a Ray community across universities, in particular research computing organizations, so that we can all work together to make Ray kind of an important tool that students learn and is available on campuses across the country. So thank you very much for your time.